Welcome to S1 Lesson 8, looking at the probability distributions, binomial and Poisson distribution. Today looking at the binomial distribution. So before you start, make sure you've got a copy of the presentation slides so you can make any notes and keep track of anything that you need to in addition to the video. And make sure you've got a pen and paper and calculator, because this shouldn't be a passive experience. You should be taking part during the video. There's questions for you to try out. Quick recap of S1. We've done the probability topic. We've done the discrete random variables topic, so now we're looking at the probability distributions, as I said, focusing on binomial distribution today. So, the binomial distribution. The binomial distribution is when we have a fixed number, n, of independent trials. So it's repeatedly carrying out the same experiment for n trials. Each of these trials has only two possible outcomes, success or failure, hit or miss, win or lose, heads or tails. All of these are binomial. Probability of success in these trials is defined as P, which is constant for each trial since they are independent. And we often note a probability of a failure as Q, and this of course is calculated by subtracting P from 1. So when we work with a binomial distribution, if X is the number of successes in n independent trials in which the probability of success is P, we must define the discrete random variable X using this statement that I have highlighted in the box. So we just replace n with the number of trials for the particular example and p with the particular probability. Here is a graphical representation of the binomial distribution. So each of these bars represents the probability of this number of successes for a certain amount of trials. I believe it's for 20 trials. So as you can see, around about the 8 mark, that would be the most likely outcome, 8 successes. And then it decreases, so when we get 1 success is very unlikely and 20 successes is very unlikely. So let's have a look at calculating some problems with the binomial distribution. First example we're going to do using first principles. So we have an ordinary 6-sided dice rolled 5 times. The discrete random variable X is the number of 6s obtained. We want to find the probability of obtaining exactly 2 6s. Now if X is the discrete random variable, it's the number of 6s I can get, these can take the values 0, 1, 2, 3, 4 and 5. We know that the number of trials n is 5 and that the probability of success is 1/6. So we'd start the question, although I'm going to do this by first principles, we should really identify the distribution. I'm rolling the dice 5 times, so that's the number of trials, and the probability of rolling a 6 is a 6th. So this is how we define and identify that we are using the binomial distribution. I want to find the probability that X is equal to 2. So first of all, I'd need to roll 2 6s. The probability of rolling 2 6s is a 6th times a 6th. So that's 1/6 squared. I must remember that I've rolled the dice a total of 5 times. So that means there will be 3 failures. And the probability of that happening will be multiplied by 5/6, the probability of a failure, cubed because there's 3 failures. There's a little bit more to this though, because if you imagine one way I could roll 2 6s is to get a 6, and then 3 non-6s in a row. Or I could do a 6, a non-6, 6, a non-6, and a non-6. I could keep on listing all these outcomes, or I could go about this a quicker way. Essentially what I'm doing here is I'm choosing 2 items. I want to know the number of combinations 2 items can be arranged out of 5. So this goes back to combinations, so I can just multiply this by 5, choose 2. If I put this all into my calculator, I can calculate an answer of 625 over 3,888. Okay, so let's formally look at the binomial formula. If the binomial formula, if X is the number of successes in n independent trials in which the probability of success is P, X is distributed binomially with n and P, then the probability of R successes, so this is what we're saying here, probability of R successes is calculated using n choose R times the probability of success to the power of how many successes we've said, times the probability of failure, multiply the difference between the number of trials and the number of successes. So let's have a look at an example. A biased coin is weighted so that the probability of getting tails is twice as likely as getting heads. If the coin is flipped 7 times, find the probability of attaining exactly 2 tails and more than 2 tails. Well, first of all, in this problem, I need to identify that actually probability of getting tails is twice as likely as heads. So if I say the probability of getting a head is X, then the probability of getting tails is 2x. Now we know that these probabilities added together gives me a total of 1. So then 3x is equal to 1 and x is equal to a third. So what I now know is that if I'm rolling the coins 7 times, then the probability of, the number of trials bx can be distributed binomially. The number of trials, is 7, just a little bit of a stutter there, and then the probability of success is 2/3 because probability of tails is twice as likely. Okay, so at this point, I can now start to calculate my probabilities. Now, part A said probability of x being equal to 2. So this would be calculated by doing 7 choose 2, multiplied by the probability of success, which is 2/3, squared, times by probability of a failure, which is 1/3, to the power of 5. So if I quickly do this on my calculator, it shouldn't take too long typing it all in. It can be typed in all in one go. Should get an answer of 28 over 729. Part B asks to find a probability that x is greater than 2. Now I could find out probability of the number of successes being 3, 4, 5, 6, 7 and add them all together. Or there's a slightly quicker way. I could do 1 minus the probability of x less than or equal to 2, which requires just the probability of x being equal to 0, 1 and 2. Now I've already got probability of x being equal to 2, so let's find out the probability of x being equal to 1. So it shouldn't take me a moment just to type that into my calculator and calculate that in one step. So probability of it being equal to x being equal to 1 would be 7 choose 1, so I should have written that down first, 2 times 2/3 to the power of 1 times 1/3 to the power of 6. When we type that into a calculator and get an answer, I get 14 over 2187. Let's do probability x equals 0. So this is going to be 7 choose 0 times 2/3 to the power of 0 times by 1/3 to the power of 7. And let's just make sure this 0 is clear that it's a 0. It's not a 6. It's just my bad handwriting. Okay, so then when I calculate this, very quickly can be done in one calculation again. It's 1 over 2187. So finally, probability x is greater than 2 can be found by doing 1 minus 28 over 729 minus 14 over 2187 minus 1 over 2187. And again, I can type this in one go. Shouldn't take me too long. And so we get an answer of probability of being greater than 2 is 232 out of 243. Okay, well I hope that made sense, because it's time for you to try one. So the discrete random variable x is distributed. So already identified the distribution for you. So we've got x is distributed binomially. So the number of trials is 10 and the probability of success is 0.4. You need to find the probability x equals 0, x equals 1, and the probability x is greater than or equal to 2. So if you pause the video at this point, have a go and then resume once you've done that question. Okay, so welcome back. Let's have a look at the solution to this. We had x was distributed binomially. Number of trials was 10 and probability of success is 0.4. So I wanted to find, first of all, probability that x was equal to 0. So we've got 10 trials, choose 0 successes, times by 0.4, that's the probability of success, to the power of 0 because there are no successes, times probability of failure, so the difference between 1 and 0.4, to the power of the number of failures, and so there must be 10 failures. If you put this into your calculator and work through it, should get an answer of 0.0060 to 4 decimal places. Part B, probability x equals 1, exactly the same, except this time it's 10 choose 1, times by 0.4 to the power of 1, times by 0.6 to the power of 9. And there's some small kind of checks you can do, like the powers here, they should add up to the number of trials, and the probabilities here, they should add up to 1. Just small things that you can double check. Now if you work through this, you should get to 4 decimal places. Probability of 1 success is 0.0403. Part C, wanted to find a probability that x is greater than or equal to 2. So following a similar logic to the previous question, I can find this by doing probability that 1 minus probability x is less than or equal to 1. So this can be done by subtracting the 0.0060, which I've already calculated, and the 0.0403 for the x is 1 and x is 0. And when you work through that, you should get an answer of 0.9537. Okay, I hope that all made sense. Now, as you can see, this is great if you just need to work out probabilities of individual items, or you're told specifically that you need to use the binomial formula, but there are quicker ways. And quicker ways are using something called the binomial tables. So let's have a look at them. So the binomial tables, they give the probability that the number of successes is less than or equal to a given value when x is distributed binomially with a number of trials n and a probability of success p. And the tables give this for various values of n and p. So if we have a look at a section of the tables, here's a section of the tables. So here is where we've got n trials. So the number of successes could be from 0 to 9. Here across here we have a probability of n, probability of the successes. So if I had, say, probability x, let's say 9 and 0.4, just for argument's sake, probability x is less than or equal to, let's say 5. Well, I'll get some different coloured pens in. What the column I'm looking for here is, I'm looking for this column here, the 0.40. Now I would use a ruler of some sort to try and do this. I mean, I'm just drawing a line on here to try and line it up. It's not a very good line, I realise that, and I'm butchering the tables. But you can see here we take a reading from the table. Now there's lots and lots of values on this table. So my advice is, I mean, the columns are not too bad to work with because there's gaps between those columns. But what I would say is use a piece of paper or a ruler to rule across and make sure that you're taking your reading accurately. Okay, so let's have a look at a question actually working with the binomial tables. Okay, example 3, we've got a discrete random variable x. It's distributed such that x is binomially distributed with 20 trials and a probability of success of 0.4. So I want to find the probability that x is less than or equal to 6. I want to find probability x is greater than or equal to 12. I want to find the probability that x is between 9 and 15. Okay, so let's have a look at the answers. Probability x is less than or equal to 6. It's a nice straightforward one to start off with. So let's go to the tables. I'm going to use a highlighter pen. Let's use yellow just so I can highlight things. We said the probability of success is 0.4. So the row that I'm looking at is right up to the yellow here. What I'll do is I'll use a green pen to rule across just so we can see the values. Now I want to do probability x is less than or equal to 6. So I'm looking across at this row here. And so the value that I'm looking at is this one at the very end, 0.2500. And actually, if I get a rubber and just clear that one up just so it's clear. There we go. And so we can see that now. It's quite clearly 0.2500. So let's put that in our answer. X less than or equal to 6, 0.2500. Now the rest of these questions require a little bit more work. Probability x is greater than or equal to 12. Well, let's have a look at the binomial distribution graph at the moment. I'm going to use a highlighter pen just to, actually I won't use a highlighter pen, we'll use a green pen. So what I'm saying is I want to say probability x is greater than or equal to 12, so I'm looking at this section of the probability here. Now, actually, my tables can only calculate the probability of less than or equals to. So what I can do instead is I can actually find out the probability from this direction, which is probability x is less than or equal to 11. And to find this probability left over here, I can do 1 minus that probability. So actually to calculate this, what I'm going to do is I'm going to say, okay, this is equal to 1 minus probability x is less than or equal to 11. Now if I go to my tables to read this off, get my highlighter pen, probability x is less than or equal to 11, so just coming across, we can see, I'm just going to stop just before the value, I get 0.9435. So let's do, this is equal to 1 minus 0.9435. And so when I do this, put this into my calculator and calculate an answer, we get an answer of 0.0565. And we are done. Okay, so again, another one which requires a little bit more work now. I need the probability of x lying from 9 to 15. So if we have a look at our table, let's identify the range that I'm looking at. So from 9 to 15, so I'm going to include 9. So this is my little line to include 9, and I'm going to go all the way up to 15. So this bit here represents probability x lies between 9 and 15. Now again, all I can calculate actually is probabilities of values lying less than a number. So what I could do is I could do from this point here, I know how to calculate probability x less than or equal to 8. And actually what I could do is if I was to calculate or use the tables to find probability of x less than or equal to 15, if I subtract probability of x less than or equal to 8 from probability of x less than or equal to 15, so I'm going to take these probabilities away from all of these probabilities here, then I get left with the range that I want. So in order to calculate this, what we're looking at is probability all the way up to this end value, but I don't want all the values up to but not including 9, so I'm going to say probabilities x less than or equal to 8. So let's go to my tables and read off those values. Again, let's get a highlighter pen so I can identify them. So I want probability x less than or equal to 15. So if I come across, I'm trying to be as straight as I can, we get 0.9997. Okay, so let's get that down. Right pen here, 0.9997. Take away. Let's go back to tables and take a reading then. We want the probability x less than or equal to 8. So here's x less than or equal to 8. Let's get a colour that's going to be a little bit more helpful. Sorry, board not being particularly responsive here. So let's come across, and so I get minus 0.5956. 0.5956, so 0.5956. And so I can just type this into my calculator now, and get a value of 0.4041. And as you can see, this is far quicker than working out all of these individual probabilities. The table has already done that for you. You're just finding the cumulative probability from that table. Okay, so I hope you understood that because time. So what we're going to do is we're going to look at something a little bit trickier now, and then I'm going to give you an example to try. So, same sort of idea. We've got the discrete random variable x is distributed such that x is distributed binomially with 10 trials and a probability of 0.2. I want to find the probability of x less than 4, and the probability of x greater than 7. Okay, so we're going to calculate these two probabilities. Probability x less than 4, so let's use a graph again to help us with that. What I'm saying is I want to know probability x less than 4. So that's probability x less than 4. So yeah, as you can see, that's actually probability x is less than or equal to 3. Okay, so let's go to my tables. I'll write that in a moment. So we know that the probability of success is 0.2. So the column that I'm interested in is up to this column here. So I'm just going to put an end marker there for myself. And I want to know probability x is less than or equal to 3. So just drawing across to highlight just so we can see where we take reading, we get an answer of 0.8791. Okay, so probability x is less than or equal to 3, and we come out with a probability of 0.8791. So not too tricky, but just got to understand how to deal with strict inequalities as well. Probability x is greater than 7. Well, let's have a look to see what happens in this situation. So let's go back to my graph just so I can identify what we're saying here. Let's use a green pen to help me identify that. So I'm saying probability x is greater than 7. So this is the point that I'm after. So what I can actually calculate on this graph is I can find this part of the graph here. Now this is probability x is less than or equal to 6. So if I do 1, take away this area, this leaves me this remaining area of probability of x greater than 7. So let's make a note of that. So actually I'm calculating this by doing 1 minus probability of x less than or equal to 6. And we can go to our tables, get a highlighter pen. I want to find the probability x is less than or equal to 6. So coming across carefully and straight is 0.9991. So we get equals 1 minus 0.9991, which gives me 0.0009. Okay, well I hope that all made sense, because now it's time for you to try out reading the tables with all these different examples. Okay, so you've been given a discrete random variable x. It's distributed such that there are 18 independent trials and a probability of success of 0.35. I want you to find the probability of all these different cases. Okay, so time for you to pause the video. Remember, you're going to need to use your binomial tables. Have a go at the question. Once you've done the question, start the video and I will go back through the solution. Okay, so let's look at the solution. Probability x is less than or equal to 7. Nice and straightforward, this one. Our tables read straight to that answer. So let's get a highlighter pen, highlight the column that I'm mostly interested in, and that's this 0.35. So I'm just going to highlight, I'm just going to put the line in just to the right of it so that I can read that value. So I know to go up to this column. Now probability x is less than or equal to 7. Just highlight across, making sure that I get a straight line. So we get an answer of 0.7283. So let's just put in that answer then, 0.7283. Okay, probability x is greater than or equal to 14. I'm going to use the graph for this last time just to highlight what we're doing here. So we want x greater than or equal to 14. So I'm saying from this point onwards here, this is actually what we want. I can't calculate this directly. What I can do though is I can do the whole probability, which is 1, and take away this area of the graph here. Now this area of the graph is represented by the probability of x less than or equal to 13. So let's make a note of that so that we know our method. So I'm going to do 1 minus probability x less than or equal to 13. it's going to be equal to 1 minus. Let's go to our tables. Let's get a highlighter pen. X equals 13. Just trying incredibly hard here. I'm kind of wandering off there. There you go. I don't think, yep, that should be. Apologies for the wobbly line. It's a bit hard to do this freehand. Get a probability of x less than or equal to 13 as 0.9997. So 0.99, one take away 0.9997 gives you 0.003. Okay, probability x lies between 4 and 8. Choose our graph to have a go at this. So green pen, I want to know what's probability. It can be equal to 4, so we're going from this part of the graph here up to and including 8. So all the way up to including here. So this is the part of the graph that I actually want to add up. So I've got probability 4 less than or equal to x less than or equal to 8. Now what I can do is I can say, okay, let's take all of this probability here. This is probability x less than or equal to 8. Except I don't want that whole probability. I want to get rid of this probability here because that's extra. So this is probability x less than or equal to 3. So in order to find probability x lies between 4 and 8, I'd have to do probability x less than or equal to 8 minus the probability x less than or equal to 3. So let's note this down in my method. So it's probability x less than or equal to 8 minus probability x less than or equal to 3. So going to my table, let's get my highlighter pen. Probability x less than or equal to 8 is just under one of my lines there, so I get 0.8609. So let's note that down while I remember. Go back to our tables. We want now probability x less than or equal to 3. So coming across as straight as I can, 0.0783. So 0.0783. So get my calculator, let's type that in and see what we get as an answer. So you should get then hopefully an answer of 0.7826. Okay, just a couple of examples left now looking at these strict inequalities. Probability x is greater than or is just strictly greater than 3. So let's have a look at our graph. Let's use that to help us. Probability x is greater than 3. So what I'm saying is here, okay, I want from this part all of these probabilities on this part here. So that's probability x is greater than 3. Now I can't do x is greater than probabilities. What I can do is I can do the whole probability, which is 1. So that's that whole probability there. Take away the first part of it, which is probability x is less than or equal to 3. So 1 minus probability x less than or equal to 3. So let's note down our technique for this, our method. 1 minus probability x less than or equal to 3. So get 1 minus. Let's take a reading from the graph. I've already got actually this done already, so I don't need to go back to my graph. I've got 1 minus 0.0783. So 1 minus 0.0783 gives me an answer of 0.9217. Okay, finally, probability x is greater than 15. So this is going to be a similar idea. One last time on the graph just to illustrate how we get this, and then from this point onwards we're not going to use this. So here's probability x greater than 15. So again I'm going to do 1 minus because I need to do less than, and what I want to do is I want to subtract this whole part of the graph here, which is x less than or equal to 15. And sorry, that green line should perhaps be over here. rather than there, so it should be probability x less than or equal to 15. I can't tell because the bar isn't there. Okay, so let's just note that down. 1 minus probability x less than or equal to 15. If I go to my table, let's have a look at my table, get a highlighter pen. If I come across to 15, you're going to see something strange happens. So come across straight, oh, there's no reading. Well, the reason there's no reading at this point is because what this is saying is actually we've got to a probability of 1.0000 from this point onwards. So although we know that this isn't certain, we know that it's not certain that you should have got a value less than or equal to 14. What we're saying is it's so close to 4 decimal places, it is certain. So actually, unusually for probability, we get an answer of actually this is going to be 0.0000. That's to 4 decimal places. It's not actually impossible to get more than 15. It's just highly unlikely. The probability is less than tenths, hundredths, thousandths, tens of thousandths. We're talking hundredths of thousandths, millionths even. Okay, well I hope that all made sense. Sometimes we need to approach the tables in a slightly different way. So using tables for probability of success being greater than 0.5, you'll notice on the tables, if we go back to the previous tables we was working on, they only go up to 0.5. So that causes a problem. So I can only find out probabilities when I've got probability of success less than 0.5. If you have a probability of success greater than 0.5, then what we do is we consider the question in reverse. And what we do is we can do this by considering the question from the viewpoint of failures instead. Okay, so let's have a look at this. We've got the discrete random variable x is distributed such that we've got a number of trials 12 and a probability of success is 0.7. And I want to find these different probabilities. Now, because the probability is greater than 0.7, what I'm going to do is I'm going to redefine a distribution. If x is the number of successes, I'm going to say y is the number of failures. Okay, so that x, sorry, not x, the whole point of this is I'm just doing it in terms of y. So y is distributed binomially. The number of trials remains the same, it's 12, but the probability of a failure is 0.3. So when I calculate probability of x being less than or equal to 5, this means I'm going to have 5 successes or less. So if the highest number of successes is 5, the lowest number of failures is going to be 15. Because what we're saying is, and I'll just write this out and show you a second, success, let's put x at there a second, and y underneath. If we have x is 0 successes, 1 success, 2 success, 3 success, 4 success, and 5 successes, then the number of failures must be 20, 19, 18, 17, 16, and 15. Okay, so what we do actually, I'm considering this, so what I'm actually saying is, okay, we want the probability that y is greater than or equal to 15. Now, the quick way of doing this is actually we just reverse the inequality and we make sure these pair sort of values add up to the number of trials. So this bit here, reverse, and then finally 5 and 15 add to n. Okay, and I'll show you that. I will illustrate that fully for this first example, but after that I'm not going to because of space. So we know probability y is greater than or equal to 15. It's greater than or equal to, so I'm going to do 1 minus. And so I want to subtract all the probabilities from before 15. So this is going to be y, so minus y less than or equal to 14. Okay, use the graph if you need to check that. So I get 1 minus, and let's go to the table and take that reading. Probability of a success we said was 0.3, so let's find our correct column. Here we go, and I'm just going to highlight again to the right with yellow just so that I can see how far to go. we want sorry, I've said 20, it should be 12. Let's just scrub that a second and change that back to 12. So this should be 12, 11, 10, 9, 8, 7. So apologies for that. I will quickly correct that. So we should have probability of greater than or equal to 7. And so if I just get this, so if I want everything greater than 7, what that means is I want to do 1 minus everything less than or equal to 6. So let's go back onto my tables now. So getting my highlighted pen, probability x is less than or equal to 6, or y, sorry, is less than or equal to 6, highlight across, I get 0.9614. So 0.9614. Okay, so stick this into our calculator. 1 minus 0.9614. We should get an answer of 0.0386. Okay, we also needed to find a probability x is greater than or equal to 4. So probability x is greater than or equal to 4. Now what I'm saying is we're going to reverse the inequality, so we're going to do y, so I'm going to say less than or equal to, and I'm going to make sure that the number that we're going to put here adds up to 12, so we're going to say x less than or equal to 8. So, I mean, if we consider what we're saying here, for x, we're saying 4, 5, 6, so on. For y, then, that means that I must have 8, 7, 6, and you can see it's less than the 6, less than or equal to 8. Okay, so this is just then a reading from the table. So let's get a highlighter pen, x less than or equal to 8, come across straight as I can, it's 0.9983. So we just get an answer 0.9983. Okay, last one. Probability x is between 6 and 10. So we're going to try and do it again without considering the values first of all, and then I'll just confirm it so you make sure that you understand it. So I've got between 6 and x is between 6 and not 18, but 10. Making up questions here. So that's going to give me y. Now, actually, I want to keep the inequality the same here. So y. Now, that means my upper boundary, that would have turned around to become the greater than rather than the less than. So what do I need to add to 10 to get to 12? It's 2. This end of my boundary, 6, that was y greater than 6. Now it's y less than, and what would I need to make that add up to 12? That's going to be a 6. Now again, if we consider the x values and the y values, what I'm saying I want x to be is 6, 7, 8, 9, 10. That means y would have to be 6, 5, 4, 3, 2, which I've represented in that inequality. The only thing that was slightly different here was I had to link these two numbers here, and then I had to link these two numbers here. But if you notice, y less than became y greater than, and y greater than become y less than. Okay, so a little bit trickier, but still the same sort of ideas. Okay, so let's take some readings from the graphs now then. From the tables, sorry, so I want y less than or equal to 6. Oh, sorry, we should actually identify how I'm going to calculate this. So this is going to be probability, not x, but y. So used to using x. Y is less than or equal to 6. Take away, well, I want to include the 2, but I don't want anything less than 2. So take away probability x, not x, keep on doing it again, take care. Y, sorry, is less than or equal to 1. So when we take our readings from the table, less than or equal to 6 is 0.9614. and less than or equal to 1. Let's get my highlighter pen so I can just read across. Here we go, 0.0850. So 0.0850. Okay, and so let's calculate that on my calculator. And you should get an answer then of 0.8764. Okay, well, aside from my little slip here where I did 20 instead of 12 for some reason, I hope that all made sense, because what we have now is an example for you to try. Okay, so for you to try, the discrete random variable x is distributed such that x is distributed binomially where there's n is 16 trials and the probability of success is 0.75. So I want you to calculate these probabilities using a reverse distribution. So pause the video at this point, and once you're done, resume the video and we'll go through the solution. Okay, so welcome back. Let's have a look at the solution. First thing we need to do, I just want to say y equals the failures. Okay, so it's important that you do things properly. You definitely need to indicate the distribution. Now, we was told that we had 16 trials and probability of success 0.75, so we're still going to have 16 trials, but the probability of a failure is 0.25. So if probability is x less than or equal to 10, then we want probability y is greater than or equal to, and it should be 6. Okay, let's double check that, x, y. So less than or equal to 10, I want 10, 9, 8. For y then, that would be 6 successes, 7 failures, 8 failures. So you can see its y is greater than or equal to 6. Now we know to calculate that, that's 1 minus because it's greater than or equal to. I want to be left with the probabilities from 6 upwards. So I want to take away all the probabilities from 5 downwards. So take away the probability y less than or equal to 5. Again, use the graph in the notes if you need to help you reason that visually. So let's go to the tables. Probability of success is 0.25. Let's get the highlighter pen out, highlight the column that we're going to be working with. Again, just going just to the right of it so I know how far to look in the table. I want probability of x at y less than or equal to 5. So coming across from y less than or equal to 5, I get 0.8103. So 1 minus 0.8103 gives me a probability of 0.1897. Okay, probability x is greater than or equal to 4. So probability y, I'm going to reverse the inequality, less than or equal to. I'm going to add this up with so that 4 plus something gives me 16. So it's going to be y less than or equal to 12. Again, we can check this. X equals 4, 5, 6 upwards. Y in that case would equal, pairing up the numbers so they add up to 12, 8, 7, 6, and going downwards. So you can see it's definitely, sorry, well, I'm adding them up to 12 there, not up to 16. Let's concentrate. So we should have actually 12, 11, 10, ... So you can see we're doing all the y values from 12 downwards. This I can read directly from the table. It's using a highlighter pen, just carefully coming across from 12. And actually, we should get probability of 1. So it's one of those unusual ones. It just happens with some distributions. So I get 1.000. Let's do it to 4 decimal places. Finally, probability x is greater than or equal to 8 and less than or equal to 13. So I'm going to say, okay, probability. I'm going to leave a space here. I'm going to say put the y. I'm going to deal with the greater than or equal to 8 because it's now going to become less than or equal to. So here's the less than or equal to. It's got to add up to 16. So 8 plus 8 gives me the 16. Now I'm going to deal with the y less than or equal to 13, changing it to a y greater than. What do I have to do to add 13 up to 16? I have to add 3. So I'm looking at the probability y is between 3 and 8. Again, let's just check that. So 8, 9, 10, 11, 12, 13. And so y, if I do them in pairs adding up to 16, I get 8, 7, 6, 5, 4, 3. And you can see I want the values from 3 up to 8. So to calculate this, I want to do probability y is less than or equal to 8. So I'm going to find the probability of all the values up to 8. But I don't want the probabilities less than or equal to 2. So I'm going to take away probability y is less than or equal to 2. So that we get, let's give myself a little bit more space there. So finding probability y less than or equal to 8, coming across quite straight there, so we get 0.9925. Minus probability of y less than or equal to 2. So highlight a pin out, let's come across. So that's minus 0.1971. And so when we put this into a calculator, 0.9925 minus 0.1971 gives an answer of 0.7954. Okay, well, I hope that made sense. Just a little bit left now, so let's have a look at the mean and variance of the binomial distribution. So, mean and variance, if a discrete random variable x is distributed binomially with n trials and probability of success p, the mean or the expectation is calculated by doing the number of trials times the probability, and the variance is calculated by doing the number of trials times the probability of success times the probability of failure. So here we have example, 5% of the hard drives produced by a company of 40 in a sample of 50 hard drives. Find the mean number of 40 hard drives and the standard deviation. So first thing to do is identify the distribution. So if we say x is the number of hard drives, and I believe it is the number of 40 hard drives. So it's important to identify what it is that your random variables represent. This is distributed, so this is definitely really important. It's distributed binomially. We are doing a sample of 50, and the probability of a hard drive being 40 is 5% or 0.05. So I want to find the expectation of x. Expectation of x we know is calculated by doing np. So the expectation of x is simply 50 times by 0.05. And actually, so it gives you an answer of 2.5. And actually, you've been working with this idea in this GCSE already. If you think about flipping a coin 100 times, how many times would you expect to get ahead? Half of that, 100 times a half, which is 50. Now, standard deviation is equal to the square root of the variance of x. So let's find the variance of x. Variance of x is equal to the number of trials times the probability of success times the probability of failure. So the variance of x is calculated by doing 50 times 0.05 times 0.95, which gives us an answer of 2.375. And so the standard deviation, square root of 2.375, won't be a second, 375, which gives us an answer of, to 2 decimal places, 1.54. Okay, hope that made sense. One for you to try now. It's slightly different, but it involves a little bit of problem solving, but there's not really hard questions based on it like on what I've just done. So this one's a good opportunity to try a little twist of a question that comes up in the exam. So for you to try now, the random variable x is distributed binomially. It has a mean of 10 and a variance of 8. We want to find the values of n and p. So pause the video, have a go. Once you've had a go, resume the video and we'll go through it. Okay, so welcome back to the video. Let's have a look at this. So we've been told we've got random variable x We know the mean, E of x equals 10, and the variance is given as 8. Now, I also know the expectation of x is defined as NP, and the variance of x is defined as NPQ. So what I actually have here is NP equals 10 and NPQ equals 8. So I've got simultaneous equations. If I divide the second equation and I divide it by the first equation, so I get NPQ over NP equals 8 over 10. What happens is the NP's cancel. This leads to a value Q equals 0.8. Since Q equals 1 minus P, this gives me that the probability is 0.2. And so I can sub that into equation 1. So what I know is that 0.2 n equals 10. So if I divide by 0.2, what we get is that n is equal to 50. Okay, really nice exam question there. It's quite often a real curveball that they can put into the paper, but it's not too difficult. Similar sort of ideas you get in C2 and many other areas of maths. Use the information you got to set up an equation. 2 variables, so it's probably simultaneous. Unfortunately, this one gives us a third variable, but that's where this third equation, or the understanding that Q is a probability of failure, come in, so that I could find P and then eventually N. Okay, well I hope that all made sense. Finally, it's now for you to do your own independent study. So have a go at the binomial distribution exercise, work on it until you feel confident. Once you feel confident with that, have a go at the binomial distribution assessment. Okay, well I hope today's lesson made sense and that you understood it all. And I look forward to seeing you in the next one.